Hello everyone, in this lesson we are going to learn analog and digital signals. This is going to be a kind of presentation. It is because of the nature of the lesson, because of the nature of the topic. In this lesson we are going to recall the advantages of transmission of data in digital form, also in analog form, and also you are going to understand the digital transmission of signal involves analog to digital conversion, also digital to analog conversion. What's an analog signal? Here is an analog signal. As you see, there is a there's a continuity of the graph, and an analog signal can be defined by the amplitude. Here is going to be the amplitude maximum value, minimum values, and it can be defined by the period, one full wavelength, also by the frequency, number of oscillations, and also the phase. On the other hand, the digital signals, they have only finite set of possible values. For example, here we have 0 and 5 volts. Okay, we have a value correspond to 5 and correspond to 0, 5, 0, 5, 0. This is a kind of a square wave. An analog wave, the analog waves are smooth and continuous. Digital waves are stepping, square, and discrete. See here, please, this is continuous and it takes infinite number of values, but this one is discrete. So this is one of the important difference between the analog and digital waves. A digital signal is a discrete representation of analog waveform. For example, here we have a if we ignore the steps here, this is going to be a analog signal. Let me draw it here. This is going to be an analog signal. But as we make it discrete, as seen here, let me make it a little bit bigger. Now, as you see here, we have discrete values in the graph. So this is the digital representation of an analog wave. Next, what is the problem with the analog signals? Here is a analog signal. It's a composite analog signal. It's not a simple. And when we transmit this signal, it is going to get weaker and weaker because of attenuation. And since it is the power is decreased, we need an amplifier or the repeater. This repeater is going to amplify our wave, and then we are going to get a wave similar to our original wave. But an analog signal picks up a noise, and the noise is amplified together with the original signal by the amplifier. This is the original undisturbed. This is the original wave, analog signal. But once it is amplified, there is some disturbance. There is some change in the wave. It creates some noise. So this is a problem in analog signals when they are amplified. A noise is the unwanted random power added onto the attenuating original signal. So this is the original signal. This is a signal attenuated because of some unwanted random power loss, and then once we amplify it, some noise is added to the system. The source of the noise is the thermal vibrations of the atoms of the medium that the signal is passing. If the signal, for example, is passing through air, the vibrations of air molecules can affect the shape, the power of the original signal. Attenuation is the gradual reduction of the signal power. The signal power, initially it has a power related to its amplitude. As you see, as it is attenuated, the amplitude is decreased. So hence the signal has to be amplified by a repeater amplifier at regular distances. Since the power is decreasing at certain distances, we need to put some amplifiers and increase the power of the signal again, but this causes some noise. This is the problem with the analog signals. What about the advantage of the digital signal? Here we have a digital signal. It's a square wave. Once we transmit it, it is also attenuated a little bit, and some noise is involved in the wave, and the regenerator, when it creates the original wave, it eliminates the noise which is interfered with the wave. So these regenerators are eliminating the noises included in the system. So a digital signal can be transmitted over very long distances. with regular regenerations without becoming increasingly noisy. There is a little bit noise here, but it is not as much as in the analog signals. Attenuation and addition of noise also happen to the digital signals, but amplified by the regenerator amplifiers. What is the advantage of the digital signal? One advantage is that the digital circuits are generally more reliable, more secure, and cheaper to produce than analog circuits. This is perhaps the main reason why almost all communication systems are digitally based in nowadays. So let's look at the conversion of the analog signal to the digital signal. So assume now we have an analog signal like this, and we have analog to digital converter, analog digital converter, ADC. This signal is going to be converted to digits, and then once these digits are produced, here is a processor. It changes the digital values to binary numbers, and then there is another converter. It is digital to analog converter. Then our original original analog wave is once more produced. Assume this is a sound wave. Here in between the first wave and the input wave and output wave, there is some digitalization, and then again we get our original sound wave. Let's look at the process of conversion from analog to the digital. So if we have, for example, such a wave, okay, assume this is a sound wave, once we convert it to a digital wave, it's going to be something like this. In an analog to digital converter, the analog voltage is sampled at regular intervals of the time. So at this time, delta t, this is another delta t, this is another delta t, at equal time intervals, we are taking some samples. We are choosing this voltage, then we are choosing this voltage, then this voltage, and this voltage. And all of these voltages are corresponding to certain values. This voltage is going to be represented by this digital value. This is going to be represented by this digital value. So what we are doing is we are taking samples from this continuous analog signal, and these samples are converted into digital output. And taking these intervals, I mean taking these samples, is called sampling, and the amount of samples per cycle is called the sampling frequency or sampling rate. The value of the sample voltage measured at each sampling time is converted into digital or binary number that presents the voltage value as it is seen here. This is the conversion of a wave, a continuous signal wave, to a digital wave. Let's look at more about analog to digital conversion. Here's an example where an analog signal is sampled at every 125 microsecond, and the digital signal recorded as 5-bit number. Here is our signal. This is a analog signal, and it has continuous values. Now we are sampling. For example, we are taking this voltage 8, but we are going to sample it every 125 microseconds. This is in microseconds. So we are going to take one sample from here, one sample from here, one sample from here. I mean, this will correspond to approximately 12 volts. I'm sorry. This will correspond to the 12 volts. I'm sorry, let me draw once more from the beginning. This will correspond to 12 volts. This will correspond to approximately 14 volts. So it is shown here. We are taking some samples. Every 125 microsecond, we are taking a sample from this curve, and these are the sample values. We are going to have these values. This is sampled. And then we are going to convert these voltages to binary numbers. So this 8 corresponds to this binary number, and this 12 corresponds to this binary number. As you see, the binary numbers are composed of only zeros and ones. Okay. Now, what is the recovered signal? This is our original signal, and we convert it, we take samples from this original sample. These are the samples, and then we convert these samples to the digital numbers. I mean, we convert to the binary numbers, and then from these binary numbers we can reconstruct our initial wave. This conversion, this sampling rate will give us this digital wave, and as you see, it is similar to our original wave, but not completely similar. So the covered signal is consisting of large steps. As you see, there are large steps here. Okay, and it can be improved. How can we improve? How can we approximate this wave? Better approximation of this wave to the original one. We need to use more voltage levels or more beats. In other words, the sampling at higher frequencies. I mean, we are going to get some other values in between these values. Here the frequency, we were taking sample every 125 microseconds, but if we, for example, take every 10 microseconds, it is going to be a very good approximation of the original wave. Let's look at the bits and voltage levels. Here is the for the 4-bit system, these are our decimal numbers from 1 to 15, and the binary numbers corresponding to these decimal numbers, the 1 is represented with 001, 6 is represented by 0110. So every decimal number has a correspondence of binary number in a 4-bit system. But if it is 8-bit system, for example, 2, the decimal number 2 is going to be represented by 1, 2, 3, 4, 5, 6 zeros, 1 and again 0. So 16, for example, is going to be represented by this number. This is 8-bit system. This means every decimal number is represented with 8 zeros or ones. Okay, the number of bits in each digital number limits the number of voltage levels. How many voltage levels are going to be taken? I mean, how many samples will be taken? It depends on the bits. I mean, 4-bit system or 8-bit system. For example, there are 4 bits. I mean, in this 4-bit system, there are 4 bits, and hence 2 over 4 will be equal to 16 voltage levels. What does this mean? If you have a signal like this and you want to change this analog signal to a digital signal, now assume these voltage levels are, let's say this is from 10 volt and between negative 10 volts. So if you are going to use a 4-bit system, you can choose 16 voltage levels to convert this analog signal to the digital signal. Let me show with a different color. Okay, 16 levels of voltages. I mean, we are going to divide between 10 and negative 10 to 16 levels. Okay, I'm going to show only some of them. So this when this wave is converted to a square wave, for example, it is going to be something like this. But okay, so there are going to be 16 voltage levels. I mean, we can sample 16 different voltage levels in this continuous wave to create a square wave. If we want to increase if we want to get a very good output wave, which is a digital wave, we need to increase the bit system. For example, for an 8-bit number system, 2 over 8 will be equal to 256 voltage levels. It means between 10 and negative 10 we can sample 256 different voltages. Then it will represent our original signal very well, and this original signal will be transmitted without any distortion. What is sampling frequency? The choice of sampling frequency also determines the amount of information that can be transmitted. The greater the sampling frequency, the more faithful is the production of the original signal. In order to recover an analog signal of frequency f, then the sampling frequency must be 2f or more. I will explain this one in detail in next slides. Now assume we have an original signal which we want to convert to a digital signal. The interval at which the signal is captured is known as sampling rate. Now we have our original signal. Now I'm going to take some samples from this signal, and the interval, I mean, if I take the samples, for example, at this interval from here to here one sample, from here to here one sample, so this is going to be my sampling interval. So this is our original wave. And now, as you see, this is one complete wave from up to here, okay, from here to here. So how many samples we have taken? This is the initial 1, 2, 3, 4, 5, 6, 7, 8, and 9 samples from here to here. So all these samples, when they are connected to each other once more, we can get the original wave again. Let's decrease the sampling rate. Now in this case, this is one complete wave, and now the sampling rate is one sample is here, and one sample is here, and one sample is here, and one sample is here. As you see, again, this one is going to represent the original wave if we connect these points to each other. In this case, here is the sampling rate. I mean, the frequency of sampling is bigger than the two times bigger than the maximum frequency of the wave. The frequency of the wave, as you see, this is one cycle. Okay, in one cycle, here we have sampled. How many samples do we have? 1, 2, 3, 4, 5, 6 samples. So, but this is one wave corresponds to only 1 hertz. Here we are sampling more than 1. So, I mean, the frequency of the sampling here is bigger than 2 times of the maximum sampling. But in this case, as you see, we have only 2 samples, one here and one here. The frequency of the sampling is equal to 2 f maximum. But now the last one, in this case, originally this is one full wave. I mean, one full wave should be here. Okay, in this interval we have one full wave, but in the sampling frequency we have one sample here, one sample here, one sample here. The sampling frequency is smaller than 2 maximum frequency. In this case, as you see, the original wave, this wave does not represent the original wave. So what does this is called? I mean, when the output wave is not representing the original wave because of the low rate of sampling, it is called aliasing. This refers to an inadequate digital sampling rate. If you have inadequate digital sampling rate, then aliasing takes place. If a signal is not sampled using enough data points, it is true frequency will be underestimated. So the true frequency of this wave, this is the original wave, is underestimated here because the sampling rate is very low here. The sampling frequency must be greater than twice the maximum frequency in order to uniquely reconstruct the original without aliasing. If your sampling frequency is bigger than 2 times the maximum frequency, assume the frequency of this wave is changing, but this is one frequency. I mean, this the constant frequency here. Assume you have a wave of this kind, for example. Frequency increases, and then frequency decreases, and then frequency decreases, and then increases again frequency. So if you have a changing frequency, but the maximum frequency, I mean the sampling frequency must be 2 times bigger than the maximum frequency. In this case, we can reconstruct our wave. Why? Because we have an original wave, and there is a converter. It is from analog to digital converter. Then it is transmitted. Then here we have from digital to analog, digital to analog converter. Then we are going to reconstruct our original wave. To reconstruct our original wave, the sampling frequency should be bigger than the maximum frequency of the wave. Let's look at one more example. For example, if you sample every cycle, this is one cycle up to here, this is one cycle. Okay, just we take one sample from here, one sample from here, one sample from here, and one sample from here. When we connect all these samples, as you see, this will not represent our original wave. And if the sampling frequency is 1.5 times per cycle, the green one is our original wave. But if a sampling frequency is 1.5, then our wave is going to be something like this. And as you see, this second wave shown with pink is not same as the original wave. Their frequencies are different from each other. That's why if you have this sound wave, green sound wave, and if sampling frequency is equal to 1.5, then you are going to get such a wave which is not going to represent your original wave. What if the sampling is 2 times per cycle? Here is one cycle. Okay, we take 2 samples. 1 sample, 2 sample. In this case, as you see, here is the 1 sample, and here is the other sample. Now our wave is going to represent the original wave as expected. But if we do oversampling, we will get a better wave which represent our original wave. Here we have oversampling. In one cycle, we have many samples. Here, many samples along this line. That's why this is oversampled. So oversampling is required to a good conversion of analog signal to the digital signal. Now, let's sample this signal periodically. I mean, if we, for example, sample every delta t like this, we are going to take a sample from here, a sample at this interval, and then a sample at this interval. If we sample every delta t interval, okay. Now we are periodically sampling the wave, and delta t is called a sampling interval, and sampling frequency, you can calculate the sampling frequency by 1 over delta t. What is the resolution of analog to digital conversion? If you use 1-bit system, this is going to be the waveform of the digital wave. But if you use a 2-bit system, this is going to be the shape of the digital wave. So if you increase the to 4-byte, it will represent the original wave better. I haven't drawn the original wave here. Assume this is our original wave. Okay. If you want to convert this wave to digital wave, in this case, if you use only 1 bit, this is going to be the shape of your wave. If you use 2-bit, this is the shape. 4-bit, 16 bits is better to represent your original wave. Okay, so as you see, here you can see that the 1 bit only has 2 levels. As you increase the bit, the levels increase, making the signal more closely represent the original analog signal. So let's summarize. In analog digital converters, 2 factors determine the accuracy of the digital value that captures the original analog signal. They are quantization level and bit rate. Okay, the quantization level or bit rate, and the sampling rate. These 2 are very important in converting the signals, analog signals, to digital signals. Now, for example, assume that 1 volt signal has to be converted from digital by using 3-bit AD converter. Therefore, a total of we are using 3-bit, so 2 over 3 is equal to 2 over 3 is equal to 8. It means we are going to have 8 different voltage levels. If our voltage, for example, is changing between from 0 to 5, it is 0, and this one corresponds to 5. Let me draw very well, I'm sorry. I mean, if this is our signal and the voltage increases from 0 to 5, I mean, this one corresponds to 5 and this is 0. And we are going to have, if we use 3-bit converter, we are going to have 8. We are going to quantize it to 8 levels. Why? Because 2 over 3 is equal to 8, and we will have 8 different samples from here to here. Okay, this result is 1 over 8 is equal to 0.25 voltages. So what does this mean? Here the 0 volt, the next voltage will be 0.125 volt. The second one is going to be 0.125. 0.125 will be 0.25. Okay, so the next one is going to be 0.25, and so on and so forth. So in the process of quantization, first we divide into the levels, and then, for example, 0 volt will be represented by 000 with 3 bits and 3 digits, and since this is a 3-bit system, 0 will be represented by 3 zeros. And the second voltage level is 0.125 is going to be represented by this binary system. And if we continue like this, for example, the 1 volt, here if it is 1 volt, not 5 volts, and we are going to divide this one into 8 voltage levels, so the 1 volt is going to be represented by 111. That's it. Thank you for listening.